Hello everyone, section 6.2 and 6.3, bisectors, medians, and altitudes of triangles. You're going to want to become familiar with what concurrent, pointed concurrency, and circumcenter mean, and what the circumcenter theorem says, because when we get to example 1, a carnival operator wants to locate a food stand so that it's the same distance from the carousel C, and from the Ferris wheel F, and from bumper cars B. Find the location of the food stand. We want to find the food stand so that it is the same distance from these three rides at the carnival. So to find a point that is equidistant between the three, that is the point of concurrency of the perpendicular bisectors or the circumcenter. The reason, and this is important, the reason that the circumcenter is equidistant from the three vertices, well, the circumcenter is the center of the circumscribed circle. So the circle that goes around this triangle and touches all three vertices is circumscribed around this triangle. The center of that circle is the circumcenter, which is the point of concurrency of the perpendicular bisectors, which means that if I draw a segment from the circumcenter to each vertex, the circumcenter to any one of the vertexes is really drawing a radius of that circle that circumscribes that triangle. And since all radii are congruent, then the circumcenter to C, or the circumcenter to F, or the circumcenter to B are all equal distance because they're all radii. So we're going to construct the circumcenter. The construction for the circumcenter is on the next page, so you can follow those directions. They use construction number 6, which is constructing a perpendicular bisector. So I'm going to construct the perpendicular bisector of BF first. Oops. So connect from here to here. And again, I'm using construction number 6, construction that you should be very familiar with at this point. And I can do the perpendicular bisector of either CF or BC. I do not have to do the perpendicular bisector of both. I can choose one or the other, because once I find where those two intersect, the third one would have to intersect at the same place. So I don't have to do both. So let's do, I'm going to do CF in this case. Now I know I'm not walking you through the construction, and that's because I've already made videos explaining, oops, I need to bring arc here for F. Okay. I've already made videos explaining how to do perpendicular bisector constructions. Right here is the location of the food stand S. SF, SC, and SB will all be congruent. And maybe if you can visualize the perpendicular bisector BC being something like this, you see that it does go through point S. Okay, so like I said, here are the instructions for the perpendicular bisector, leading us into example 2, which is actually a fairly challenging problem. We're going to do some coordinate geometry here. We want to find the coordinates of the circumcenter of triangle DEF, where we're on a coordinate plane. We have the coordinates for D, E, and F. So to find the coordinates for the circumcenter, we need to find that intersection point of these two perpendicular bisectors, right? Perpendicular bisector, perpendicular, bisector. So, but we're going to do that, this time we're going to do it using algebra, so algebraically, on the coordinate plane. So how do we do that? We need to find the equation of each of these two perpendicular bisectors, and then we're going to find where those equations, the equations of those two lines, intersect. Now in this case, it's going to work out to be fairly easy one to do. In fact, if we were to graph it, it would be a very easy one to do, but I don't want to graph, I want to take you through the algebra of it, because when you're doing some of these problems in the bookwork, you won't be able to just take a look at the picture. You're going to have to do the algebra occasionally. So, to do the algebra, to come up with the equation of the perpendicular bisector, we need to find the midpoint of segment DE, or midpoint of EF, or the midpoint of DF. Let's start with DE. So the midpoint of DE, the average of the x's, so 6 plus negative 2 is 4, divided by 2 is 2, and the average of the y's, 4 and 4, is 4. So the midpoint of DE is 2, 4. We also need to find the slope of DE. Slope is always indicated with the letter M for the Latin word for slope, which is mont, mountain, mont. So M being slope of DE, slope is going to be y2 minus y1 over x2 minus x1, or 0 over negative 8, which is 0. But I want the slope of the line perpendicular to DE. So the slope perpendicular to DE. So perpendicular to a line that has a slope of 0 is a line of slope that is undefined. Okay, so lines that are undefined sloped are perfectly vertical lines. Zero slopes are horizontal. Vertical lines have a slope that is undefined. Vertical lines have equations that are x equals whatever the x value is for every point on that line, and where it crosses the x-axis. So we know that the line goes through this point, 2, 4. So the equation for the line perpendicular to DE through the point 2, 4 is x equals 2. We have to do this again and then find where this line intersects the second line. So I'm going to do it for EF. I could do it for DF. I'm going to do it for EF. So the midpoint of EF, average of the x's, negative 2 and negative 2 is negative 2. Average of the y's, 4 plus negative 2 is 2, divided by 2 is 1. So the midpoint of EF is negative 2, 1. Slope of EF is y2 minus y1, negative 2 minus 4, negative 6, over negative 2 minus negative 2 is 0, which is undefined slope. Slope perpendicular to EF is therefore 0. This time we have a perfectly horizontal line. Lines that are horizontal are y equals, and in this case, y equals 1 because it has to go through the point negative 2, 1. Y equals 1. So where does the line x equal 2 and y equal 1 intersect? X equals 2, y equals 1. Therefore, they intersect at 2, 1. And there is the circumcenter, the coordinates for the circumcenter. Now, more often than not, the equations are going to be a little bit harder here, and you're probably going to have to use substitution or combination, most likely substitution, because you probably get an equation that is in slope-intercept form or point-slope form here, point-slope form here. Pretty easy to get them and do substitution. Once you've done the substitution, you should be able to come up with either the x-coordinate or the y-coordinate, plug that back into the equations, and you'll get the other coordinate. That is example 2. Example 3, we're now working with the incenter. Okay, the incenter is the point of concurrency of the angle bisectors, not the perpendicular bisectors. This time it's the angle bisectors, which is construction number 3, a long time ago. And the incenter is equidistant not from the vertices, like the circumcenter was, but the incenter is the center of the inscribed circle that touches the 3 sides at one point. We're going to learn that that word's called tangent. When the circle touches a line at one point, it's tangent. The line is tangent to the circle. So that makes n the center of the inscribed circle. That makes n equidistant from the 3 sides because NE, NF, and ND are all radii. They're all congruent. That's the incenter theorem, and that's the reason why the incenter theorem is what it is. So that means that NE and NF are congruent to each other, and we can come up with the equation 6x plus 1 equals 4x plus 15. Subtract 4x, subtract 1, 2x equals 14, x equals 7. If x is equal to 7, 6 times 7 plus 1, then NE, NF, and ND are all equal to 43. Now, can NB here be 40? And the answer is no. Why? If NB was triangle NBD is a right triangle. We already know ND has to be 43. NB is the hypotenuse. The hypotenuse can't be smaller than the legs. No. The hypotenuse cannot be shorter than either of the 2 legs. Okay, and we already know that ND, which is one of the legs, is 43, so NB cannot be 40. All right, practice your constructions. For the end of the chapter, you'll have a constructions quiz. Example 4. A school has a fenced-in area in the shape of a scalene triangle for the use of new playground. The school wants to place a swing set where it will be the same distance from all 3 fences. Should the swing set be placed at the circumcenter or the incenter of the triangular playground? So the circumcenter is going to be equidistant from the 3 vertices. The incenter is going to be equidistant from the 3 sides. Therefore, incenter is the correct answer. All right, centroid. Centroid has another name. The centroid's second name is called the center of gravity. It's actually the balancing point of a triangle. If you find the centroid or center of gravity, I can cut this triangle out and it would balance on the tip of this pencil on point Q. The other neat thing, which is the centroid theorem, is that the centroid divides the median, UT, into 2/3 and 1/3. QT is 2/3 of UT. QU is 1/3 of UT, which means QV is 5, RQ is 10, and RV is 15. Pretty simple and straightforward. Again, construction for the centroid. And example 6. Now, in example 6, our textbook wants you to find the coordinates of the centroid the same way that we found the coordinates for the circumcenter. It wants you to find the equation of the median that connects from A to the midpoint of BC, and the equation of the median that connects from B to the midpoint of AC, or the equation for the median that connects C to the midpoint of AB, and then find the intersection of two of those three equations, which will be the centroid. Or, I'm showing you a shortcut. It's a very handy shortcut. It's going to save you a ton of time. There's a formula. There's a formula for finding the centroid. So the centroid is x3 plus x2 plus x1 divided by 3, comma, y3 plus y2 plus y1 divided by 3. Or in this case, let's go 7 plus -4 plus 0 divided by 3, comma, 1 plus -2 plus 4 divided by 3. This is going to be 3 divided by 3, or 1. And here we get -1, also 3 divided by 3, which gives us another one. So the centroid is 1, 1. Way easier than finding the equations of the lines. So use that formula. It's going to save you a lot of time. Okay. Find the coordinates of the centroid DEF. So let's use that formula again. 4 plus -4 plus 0 divided by 3, comma, 6 plus -2 plus 6 divided by 3 gives me 0 divided by 3, comma, 10 divided by 3, or 0, comma, 10/3, or 3 1/3. I will take either version of the equation, of the final coordinates. Alright, prove that the bisector of the vertex angle of an isosceles triangle is an altitude. So, in order to do that, I'm going to give you a diagram here. And let's call this A, B, C triangle. And we're going to do the bisector of the vertex angle. So first we're going to have to make this triangle isosceles. And then I have to bisect it. Point D here. If I bisect it, I'm going to have congruent. Okay, our goal is to prove that ADB or CDB is a right angle. Okay, well, what do we know about triangle ADB and triangle CDB? If we look at the diagram, I see side, angle, side, side, angle, side, right? BD is congruent to itself. These two triangles are congruent by side, angle, side. These two angles are congruent by CPCTC. They're also forming a linear pair. Two angles that are congruent and supplementary have to be right angles. Therefore, BD has to be an altitude. So the rest is just writing it out. And I wonder if I can fit it all. I probably can't fit it all in one. So I'll leave myself room in case I need to make a second. So one, we are given triangle ABC is isosceles. And BD bisects angle ABC. That's given. 2. Angle ABD is congruent to angle CBD. D. Definition of an angle bisector. I'm definitely going to need the second columns here. Statement 3. BD is congruent to BD. Congruent to BD. Flexive property. I almost forgot. ABC is isosceles. AB is congruent to BC. AB congruent to BC. Definition of isosceles. Okay. Statements, reasons, continued. So statement 5, triangle ABD is congruent to triangle CBD. Side, angle, side. 6. Angle ADB and CDB. Angle ADB is congruent to angle CDB. CPCTC. CPCTC. Right? Also, they form a linear pair. Angle ADB and angle CDB. I'm actually going to run out of space. Are a linear pair. Definition of a linear pair. Okay. Finish it off up here. Statements, reasons. So statement 8. BD and AC intersect to form I changed my mind. Angle ADB and angle CDB are supplementary. definition of linear pair. Linear pair postulate, the LPP. Linear pair postulate, the LPP. 9. Angles A, D, B, and angle C, D, B are right angles. 2 angles that are congruent and supplementary are right angles. It's one of our theorems that I can't recall the name of right now. 10. BD is an altitude of triangle A, B, C. Definition of altitude. Q, E, D. Okay. Orthocenter is the last of the centers of a triangle. It's formed by the intersection of the 3 altitudes of a triangle. It's point of concurrency for the altitudes of a triangle. It is the center of another circle. So the circumcenter is the center of the circumscribed circle. The incenter is the center of the inscribed circle. The centroid is the center of gravity. And the orthocenter is the center of something called the 9-point circle, which is not interesting or important in any way, shape, or form. The orthocenter doesn't get a theorem that's associated with it, like the median being the 2/3 theorem, or the incenter being the equidistant from the 3 sides, or the circumcenter being equidistant from the 3 vertices. The orthocenter doesn't get anything fancy like that at all, but it does play a role in something called Euler's line, which we're going to get to in a second. All right, example 9 here. Example 9, we get the points of concurrencies here are drawn for 2 different triangles. All right, we want to match the points with the lines and segments listed from 1, 2, 3, and 4. 1 being the perpendicular bisectors of the sides, 2 being the angle bisectors, 3 being the medians, 4 being the lines containing the altitudes, or circumcenter, incenter, centroid, orthocenter. Okay, so point A is that perpendicular bisectors of the sides. Well, doesn't look to me like it's, if I draw the perpendicular bisectors, perpendicular bisector, perpendicular bisector, that looks like point C. So I'm going to say C. I take that back. I'm going to say C is the median. So we've got A, B, C, D. This is a right triangle, and if we play the outside inside on game, the circumcenter of a right triangle is on the right triangle, and specifically it is on the midpoint of the hypotenuse. So D is the perpendicular bisector or circumcenter. Okay, playing the outside-inside-on game. The orthocenter for a right triangle is also on the right triangle, and specifically it is on the vertex of the right angle. So A is Roman numeral 4, the lines containing the altitudes, or the orthocenter. That leaves us with B and C. Again, outside-inside-on game. It's a right triangle. The in-center and centroid are actually always inside of the triangle. Whether the triangle is a right triangle, acute triangle, or obtuse triangle, doesn't matter. The center of gravity, or medians, point of concurrency of the medians, is always got to be inside the triangle. You can't have the center of gravity of an object be outside of the object. And the angle bisectors, well, the angle bisectors always go through the triangle, so the angle bisectors will always intersect inside the triangle. So angle bisector B is the angle bisectors, Roman numeral 2, which is the in-center. Which leaves 3 for C, the medians. And I'm labeling these a little bit more because when we do example 10, we're going to need to know these. And over here, for this triangle, which is an obtuse triangle, A, B, C, and D. Okay, so this one's obtuse, playing the outside-inside-on game. The circumcenter of an obtuse triangle is outside of the triangle. The circumcenter for an acute triangle is inside the triangle. So the circumcenter, or the perpendicular bisectors of the sides, is either A or D. So if we look at perpendicular bisector, two of these sides, that's A, or circumcenter. Okay, B and C are both inside. They're inside no matter what type of triangle it is. So B and C are the in-center and centroid. So B is going to be, if I connect to the medians, the midpoints, B is the medians, or centroid. Medians here, I meant to write centroid. All right, C must be the angle bisectors, or in-center. And D is outside for an obtuse triangle. Orthocenter and circumcenter are outside of obtuse triangles, inside of acute triangles, on right triangles, and on those 2 points that I already mentioned in part A here. So D is the lines containing the altitudes, right? If I continue this and then draw the altitudes, can go through D, which makes it the ortho center. There's example 9. Now, why did I label all of these? Because I'm going to go back to this picture, these two pictures, in a second, after I read example 10. History. In 1765, Leonhard Euler, one of the most notable mathematicians, he wrote a tremendous amount of textbooks on math and science. He gave us quite a bit of the notation that we use in math and science. He gave us the letter I, which you're going to learn about when you take Algebra 2, standing for an imaginary number. He gave us a lot of notation that we use in calculus. And after he passed away, mathematicians got together and said, well, Leonhard Euler gave us so much, we're going to give back to him. So like we have the number pi, which we indicate with the Greek letter pi, there is a number that you're going to learn about next year in Algebra 2 that is called E. And it's called E in honor of Leonhard Euler. Mathematicians decided to give him a number, name a number after him. So, proved that for any triangle, 3 of the 4 points of concurrency are always going to be collinear. The line that contains these 3 points is known as Euler's line. We're going to go back to example 9 and determine which point of concurrency does not necessarily lie on Euler's line. So, what do I mean by Euler's line? Collinear. So we've got these 4 points, A, B, C, and D. A, B, C, and D. Looking at the diagrams, Leonhard Euler looked at these and noticed, you know what? These 3 are collinear. These 3 are collinear. And no matter how he drew the triangles, 3 of the 4 are always collinear. Now, occasionally, all 4 of them are collinear. If the triangle is isosceles, all 4 of them are collinear. If the triangle is equilateral, equiangular, regular, then all 4 points are actually the same point. They're 1 point. But no matter what the triangle looks like, 3 of the 4 of them, if it's scalene, are guaranteed to line up. And that line we call Euler's line. So if we connect here, Euler's line, connect here, Euler's line. But one of these points isn't on this line. One of these points over here isn't on this line. Wouldn't it be neat if it was the same point both times? Well, B in part A was the incenter. C in part B is the incenter. Incenter is not always on Euler's line. Sometimes it is, but not always. So here's a summary of all the information from this unit. Now, something that was accidentally left out of this unit and is left out of our textbook, and more importantly, is left out of my notes, and I'm going to rectify that right now, is how to construct the orthocenter. We have constructions for circumcenter, incenter, and centroid. We don't have the construction for the orthocenter, so let's do that right now. To construct the orthocenter, we're going to use construction number 5. So I'm going to draw any triangle, nothing fancy, just a random everyday triangle. I'm going to try to make it, scalene, but not a right triangle. I want it to be fancy. Okay, so here we have a triangle. Let's call it A, B, C. I'm going to grab a pen here, and I'm going to construct the 2 of the 3 altitudes. I'm not going to do all 3. I'm going to do 2 of the 3 altitudes, and that will find the orthocenter, or the center of the 9-point circle, which I will not show you how to do that. You can look it up if you want to. I have seen it done once, And I'll never get that part of my life back because it actually was kind of pointless. So, I need to construct a perpendicular through point B, perpendicular to line AC. To do that again, we're going to use construction number 5. And I'm going to make sure that line AC is long enough to do this easily. So I'm just extending line AC just to make sure. So to do this, we're going to put our center of our rotation at B. And I need to draw an arc that is going to intersect line AC, not segment AC, but line AC at 2 points. Here and here. Okay? Now, I've got these new 2 points, and this is construction number 5, constructing a perpendicular from a point to a line. Now I want to do the perpendicular bisector of these 2 points. This point and this point. So, let's do that. Set my center of the arc here. Make sure I'm beyond halfway. And I'm actually only going to do my arc down below here. Oops. Because I already have point B. I just need the intersection of these 2 arcs. Be careful, don't put your center on C. Put it out here where you have hit the line, wherever that may be. There's my arc, and I can connect from B through that intersection. That is going to be a right angle. I have missed a little bit here, sorry. Rectify that. There we go. Now, I got to do the same thing for either line B or line C. So C to AB or A to BC, one of the two. Really doesn't matter. Let's do C to AB. And again, I'm going to extend line AB just to make sure that when I do the 2 arcs, the arc coming from C, that it's going to hit line AB. So all I did was extend BC. I'm going to put my compass here on point C. And I'm going to make the intersection, 2 of them, one here at AB and one here at AB. Now I need to do the perpendicular bisector of these 2 new points, this point here and this point here. Okay, see that? Good. Put the center of rotation here, make sure I am beyond the midpoint. And again, I don't need to do an arc that goes up and down. I just need to do an arc on the opposite side of point C so that I can connect C to the intersection. Come down here, don't put it on A, don't put it on B. Put it on the intersection of the arc and the side. Draw my arc. Hopefully I met. I did. Yay. Connect from C through the intersection of these 2 arcs. Okay, I think I hit it. Yep. There. Right angle. And there is our orthocenter. And there is the construction for the orthocenter. You won't find this one in the book. You won't find it in my notes, unfortunately. But that is how you construct the orthocenter. And it will be on the constructions quiz at the end of the chapter. Thank you very much. Bye.